Welcome to Grandeur Decoded, where we dissect the world's most spectacular achievements and explain the engineering and logistics that make them work. Las Vegas Sphere looks like a simple curve. In reality, it is a precision machine wrapped around a stadium, built in a desert, and asked to stay aligned under heat, wind, vibration, and daily show schedules. It stands about 366 feet tall and about 516 feet wide. Its exterior LED surface is commonly described as about 580,000 square feet. Inside, the media plane is about 160,000 square feet, and the venue is designed for roughly 18,000 guests. For this to feel seamless, the structure has to behave on purpose, and it has to do it while carrying enormous weight. Reporting on the build describes a roof steel system on the order of 13,000 tons supported by a gridded steel exoskeleton. That is not a skin. That is a load. Here are 10 decoded facts that explain the specific engineering moves that made it workable. Fact 1. The foundation is 2 concentric rings of deep piles because a sphere punishes uneven support. Sphere's foundation uses 24-inch diameter auger cast-in-place piles that extend as deep as about 100 feet into dense bearing soils. The piles are arranged in 2 closely spaced rings at the perimeter. The outer ring supports the outer venue columns and the base of the exterior shell. The inner ring supports an inner line of columns. Individual pile caps also support the seating bowl and concourses. That double ring matters because lateral loads on a curved form create both overturning and torsion. The building wants to rock and twist. 2 rings widen the stance against torsion and reduce the risk of differential settlement that would warp the curve. The major concrete shear wall cores sit on pile-supported concrete mats that are roughly 4 feet thick, helping resist overturning moments and shear. Fact 2. The venue is its own concrete and steel building, stabilized by concrete cores and diaphragm rings. From the ground to about the 5th level, the venue is framed in concrete slabs, beams, and columns. Above that, structural steel takes over. The seating bowl is supported by raker beams carrying precast concrete stadia units. The main lateral system is 4 cast-in-place concrete shear wall cores, plus a proscenium shear wall at the stage. The load path is specific. The concourses collect lateral forces and deliver them into diaphragm rings at each level. Those rings distribute the loads and drag them into the cores and stage walls, instead of letting a few isolated frames take everything. Over the stage opening, 2 composite concrete and steel transfer girders span the proscenium to create a column-free opening, while also controlling differential settlement for dome roof columns transferring at that elevation. That is how you protect sightlines without turning the roof into a structural compromise. Fact 3. The dome roof is a 440-foot diameter arch system, and its base acts as a tension ring to stop the dome from pushing outward. Above the venue sits the dome roof, a steel-framed structure about 440 feet in diameter. It supports the suspended media plane plus catwalk and AV loads. A dome naturally pushes outward at its base, so the flat roof at the base of the dome acts as a tension ring that resists that thrust. That keeps the primary gravity load path more vertical, which is a friendlier problem for columns and foundations. Now the interface detail that matters. The roof connections allow radial movement without restraint, but circumferential restraint is locked so lateral loads, especially seismic loads, can be delivered into the venue diaphragm rings and then into the concrete cores and walls. The roof can breathe in and out with temperature, but it cannot slide around the circle. Flexibility prevents thermal damage. Circumferential locking preserves the lateral load path. Fact 4. Erection tolerances were inches, but the media plane needed fractions of an inch, so they hung a precision structure under the roof. The dome roof steel was expected to land within about 3 inches over roughly a 400-foot span. Reported erection accuracy was closer to about 1 inch, excellent for steel at that scale, but still not enough for a high-resolution LED surface where tiny steps become visible. Engineers solved that gap with layering. Under the dome roof steel, they added a hung grillage supported off the roof frame. That grillage supports the media plane structure, catwalk system, and AV equipment. Under that, additional media plane support layers refine the geometry again. Each layer acts like an adjustment stage, stepping down from inch-level steel reality to fractional inch tile alignment. This matters because the interior screen is not one panel. It is built from many tiles, often reported around 64,000 separate LED tiles. If the support surface is even slightly off, tile edges reveal the structure you were trying to hide. A 10-inch thick concrete slab on metal deck, placed by shotcreting where steeply sloped, adds permanent stability and acoustic damping to the roof assembly. Fact 5. Field connections were bolted, not field welded, to avoid locking distortion into a huge curved frame. All field connections of the dome were bolted rather than field welded. Field welding introduces heat and shrinkage. On long curved steel, shrinkage can pull geometry off target and add locked-in stress. Bolted field connections are inspectable and correctable during erection. If geometry drifts, crews can adjust instead of cutting out welds. Fact 6. The exterior shell uses a geodesic triangle lattice because triangles keep a curve stiff with less material. A triangular lattice spreads wind suction and wind pressure around the curve and prevents local soft spots that would ripple into visible facade misalignment. Triangles resist deformation because their geometry cannot change without changing member length. It also creates a repeatable attachment grid. A spherical display needs millions of stable mount points that do not creep under load. Fact 7. The exosphere is about 1.2 million LED pucks, and that count forces a maintenance and thermal strategy. Sphere states the exosphere has about 1.2 million puck-shaped LEDs spaced about 8 inches apart. Each puck contains 48 individual LED diodes. At that scale, even a tiny failure rate becomes routine work. The display must be zoned so failures stay local, and replacement is possible without disturbing large areas. Thermal management matters too, because heat changes dimensions, and dimensional drift shows up as visible misalignment on a curved display. Keeping temperatures and interfaces stable is part of keeping imagery crisp. A subtle structural choice was isolation. Engineers described keeping the venue structure isolated from adjacent connected structures so forces do not pass back and forth, avoiding a podium backstay effect where one building unintentionally braces another and drags loads through connections never meant to be primary. Fact 8. Heat management is structural management because temperature gradients create stress and change alignment. Different parts of the sphere heat up at different times. One zone wants to expand while another lags behind. If you lock everything rigidly, stress concentrates at the weakest joint, so the building is designed to move where it can and stay locked where it must. The dome roof interface shows the philosophy. Allow radial breathing while preserving the locked path for lateral load transfer. On the exterior, heat from LEDs adds to the gradient problem. Managing airflow and interfaces helps prevent hotspots that would drive localized expansion and concentrate stress in the wrong details. Fact 9. The interior screen and the audio system are mechanically linked because vibration and precision do not coexist by accident. Reporting on the venue describes an audio system on the order of 167,000 speakers hidden behind the screen, using hollow plot technology to steer sound. That means the media plane is not only a picture surface. It is also a structural layer sitting in front of a dense array of hardware. If the media plane shifts, you risk visible seams, vibration, rattle, and fatigue at attachments, plus changes in acoustic behavior. That is why interior surfaces in the bowl are designed to absorb or diffuse sound, with only specific reflectors used for targeting. The building can only behave like a precision instrument if the structure keeps those layers stable. Fact 10. Construction sequencing was treated like assembly because a sphere cannot be allowed to drift during erection. Pairs of adjacent half arches with intermediate framing and temporary tie rods were prefabricated into units and lifted into place between perimeter columns and a temporary center shoring tower. That modular approach limited cumulative error. Temporary support was removed only when the ring and arch system could close and carry itself. On this geometry, sequence is structure. The reason the Las Vegas sphere works is not one clever trick. It is a chain of decisions that protect geometry, from deep piles to diaphragm rings to a dome roof that can breathe without losing its lateral load path, to a hanging support system that turns inches into fractions of an inch. If you want more episodes that stay concrete, specific, and mechanically honest, subscribe to Grandeur Decoded. We explain the mechanism